Hi, today I'm going to do a little bit revision of my maths course. Alright, so for the first chapter, we have learned about Fourier series. Okay, so Fourier series. So this is Fourier series, right? So this is the first chapter. So what's Fourier series all about is basically it's just a ordinary series, right? So it's an ordinary series where for a periodic function f of x, for example, so let f of x periodic, okay, let f of x periodic within a period t, with period t, okay, then f of x uh, we can represent f of x as Fourier series like this. Okay, so we start with a naught plus sigma summation of n starting from 1 to infinity, a constant a n, cosine n pi x, sorry n, okay, n pi x divided by l plus constant bn sine n pi x divided by l, whereby where, okay, where a naught, a n, and bn are Fourier coefficient. Okay, and with L equals to half of the period t. Okay, that's all. So that's all about Fourier series. So it's just a series like Taylor series, a Maclaurin series, infinite series, and so on. But here we have a periodic series. Why? Because we have this kind of periodic function which is cos and this sine, okay, sinusoidal function which is periodic. So one way in order for us to represent the function f of x, it must satisfy first condition, which is it has to be periodic with period t. Okay, that's all. So let's find how to find the constant a naught first of all, right? So a naught, we have a formula. So formula which is let me use, so a naught is basically 1 over 2l integration from minus l to l. So l is the half of the period. Okay, f of x with respect to x, right? What about an? So an occurs 1 over l integration minus l to l f of x times cosine of n pi x divided by l with respect to x. Okay, and lastly is bn, which is 1 by l integration minus l to l f of x sine n pi x divided by l with respect to x. Okay, so this is our key to answer any Fourier series question. Okay, so let's try to attempt a simple question first. Okay, let me find question if I can. Okay, so I have over here the question, so let's try to answer it. So this would be the first question. So expand f of x equivalent to x sine of x with the range interval from minus pi to pi. Okay, using Fourier series, using fs or Fourier series, right? Okay, first, because we are integrating within minus pi to pi, so we know the period is 2 pi. Okay, because if you draw a graph, simple 1D graph like this, so minus pi to pi, so this is 0. So how many pi, or how many time or period from minus pi to pi? It is 2 pi, right? So that's why the period is simply 2 pi. Thus we can say that the value of L in this case is pi. Okay, so that's first thing that we need to find, the period or the value of L. And then since we know that we are integrating from minus pi to pi, so we can take advantage of this by considering either f of x even or odd. If f of x even, then there is no sine term in the Fourier series. Else, if f of x is odd, then there is no cosines term in the series, right? So let's consider f of x equals to x sine of x. Then we try substitute f minus x, so it's minus x sine minus x, so this is minus minus plus, so x sine x. Hence we see that fx, the function, is equivalent to the function f minus x, which tells us that it is even function. Okay, so no sine term in the Fourier series. Okay, what constant or coefficient contributes to the sine term? It is over here, right? So we know that the coefficient Bn should be 0 automatically. Bn equals to 0. Okay, so we just reduce the work for us to work of calculation to find Bn, because we don't have to find it, because we already proved that there is no sine term in the Fourier series, because it is f of x is an even function, right? So we need to find a naught. So a naught, what is a naught? Is simply 1 by 2L integration minus L to L f of x dx. So we know L is pi, so 1 by 2 pi integration minus pi to pi, f of x is x sine of x dx, right? Okay, so we need to use integration by path, of course. So 1 by 2 pi, so let me quickly evaluate this integration by path. So first, plus x, okay, integration of sine x is minus cos x, right? So minus cos x divided by the integration of the inner function is 1. We don't have to write it 1. So minus, okay, derivative of x is 1, integration of cos, so integration of minus cos is minus sine, so plus sine of x, evaluating from minus pi to pi. So we already see that for any sine of pi and sine of minus pi, it is 0. So we don't have to consider that, because if you remember, sine is like this and pi is over there. So sine of pi or minus pi is 0, right? So we just work with the cosine of x over here. So 1 by 2 pi. So substituting pi minus pi, cosine of pi minus, okay, masuk, we just insert the minus pi, cosine of pi, like that. So okay, so a naught is 0. Interesting. Okay, so an is 1 by L, integration minus L to L, f of x cos n pi x by L dx. Okay, L is pi, integrate from minus pi to pi, f of x is x sin x cos nx dx. Okay, so we have sine and cos, so we need to combine this first. So let's do another work. So recall that sine a cos b. So using the product to sum formula is 1 by 2. I already forgot this. It's sine, right? So it's sine a plus b minus sine a minus b. Wait, let me check first. I'm not very sure with this, my sum of, product to sum formula. Hopefully I'm correct. Product to sum. Okay, yeah, so sine a cos b is half sine a plus b. Oh, sorry, so this is supposed to be plus. All right, so yeah, that's all I'm just missed. Okay, so let's evaluate that. So if we have sine x cosine x, sine x cosine x is just half sine a plus b, so x plus n x, which is n plus 1 x, betul, is it right? Okay, betul, right, plus sine n minus 1 x, is it? Okay, I'm sorry, 1 minus n, 1 minus n. Okay, so it's x minus nx, right? Yeah. Okay, what else? We can substitute inside there. So 1 by 2 pi x, wait, let me check, x sine n plus 1, so integration x sine n plus 1x dx. So this is the first integration, minus pi to pi plus integration x sine of 1 minus nx dx minus pi to pi so integration by path again, 1 by 2 pi so plus x, integration of sine is minus cosine, so minus cosine n plus 1 x divided by integration of the inner function, which is n plus 1 itself, minus derivative of x is 1, integration of minus cos is minus sine, so it's plus sine n plus 1x divided by n plus 1 square from minus pi to pi. Okay, let me see. Okay, so this is pretty similar, plus minus x cosine 1 minus sorry, where is it, cosine n minus 1 minus n 1 minus n x divided by 1 minus n plus sine 1 minus n x 1 minus n square. So I can shift this n 1 minus n to be n minus 1 because cos is an even function, and this also n minus 1, but because sine is odd function, so we need to put the minus sign there. Okay, and also because this is square, so we can just flip them around, this flip them around with the minus sign, minus minus is plus, right, like that. Okay, so yeah, just insert the plug in the value, so 1 by 2 pi okay, minus pi cosine n plus 1 pi n plus 1. So of course, because sine is 0 of any multiple of integer of pi, so we expect this to be all 0, and this also 0. So okay, so I already knew about that, from minus pi to pi. So yeah, so minus minus pi, so plus pi cosine n plus 1 pi over n plus 1. Okay, hopefully I'm not doing any mistake, plus cosine n minus 1 pi n minus 1 minus, which is plus, so it's supposed to be minus, right? Minus, so minus pi cosine n minus 1 pi over n minus 1, like that. Let me check if I'm doing any mistake. So it's minus, oh yeah, I think I'm wrong this. Wait, I'm confused. Minus, it's plus pi cosine n plus 1 pi n plus 1, like that. So 1 by 2 pi, so it's minus 2. So let me write this first, because it's plus 2 pi cosine n minus 1 pi n minus 1, then minus 2 pi cosine n plus 1 pi over n plus 1. So this is our final, not final actually, this is the n. Okay, let me see what I can simplify a bit. 1 by 2 pi, so we can we can eliminate this 2 pi. It's become cosine n minus 1 pi n minus 1 plus cosine n plus 1 pi n plus 1. Okay, so what I can do here is express cosine n plus minus 1 to be in what form. Alright, so my god, I already forgot this. Okay. So cos, okay, let me do any sketch. N pi minus pi is cosine n pi sin pi plus sine cosine pi plus sine n pi, which is 0, so that's 0. So cosine pi is just minus 1, so this is minus cos n pi, right? So minus cos n pi minus cos n pi minus n minus 1. So that one. Okay, what about this? So it's cosine n pi cos pi minus sine n pi, which is 0. So this is also the same, right? Minus that, so we know it's supposed to be plus cosine n pi n plus 1. Okay, but we know that cosine n pi is just minus 1 to the n over n minus 1 plus minus 1 to the n plus 1, like that. Okay, yeah, so this is interesting. Multiply n plus 1 plus minus 1 and minus 1 over n square minus 1, like that. So I'm not sure if this will work. Let's see. Minus 1 to the n times n minus minus 1 to the n plus minus 1 to the n times n minus 1 to the n over n square minus 1. So this is the method of simplification only, but let me see. Minus 2, okay, minus 2 minus 1 n plus 1. Well, I think I don't have to do like this. I think so. Let's do like this instead. So if n is odd, first even, we try even, which is, if even, then we have minus 1 over n minus 1 plus 1 over n plus 1, like that. So we'll have n plus minus n minus 1 plus n minus 1 n square minus 1, which is minus 2 n square minus 1 minus 2 n square minus 1. If n is odd, which makes this is plus, that one is minus, so the whole thing change. So n plus 1 minus n plus 1 over n plus n square minus 1. So it is 2 over n square minus 1. So that's all. Yay! So we already solved this basically. So okay, so f of x, we can express it as a naught just now is 0, right? So 0. So we just left with sigma n equals to 0 to infinity a of n cosine n pi, like that. So bn is also 0. So an is we have two possibility, odd and even. So minus 1 to the n minus 1 plus minus 1 to the n plus 1 cosine nx. Okay, so let's substitute several value. When n equals to 1, sorry, n starts from 1, n starts from 1. So when n equals to 1, so we have to use this odd possibility. So 2 over, oh yeah, n cannot be 1. Okay, so we need to start from even term, which is 2. Okay, with the indication n cannot be 1, like that. So we start from even, so we need to consider the first possibility, which is even, like that. So n equals to 2, so it's minus, right? So let's bring minus sign in to the outside. So okay, we just bring 2 also and the minus sign, so it's 1 by n square minus 1. So 2 square is 4 minus 1 is 3, so 1 by 3 cosine, sorry, am I correct? Cosine 2x minus n equals to 3, which is odd, so 1 by 3 square is 9 minus 1 is 8, 1 by 8 cosine 3x plus, so this is alternating plus and minus sign. So n equals to 4, which is even. 1 by 4 square minus 1 is 16 minus 1 is 15. 1 by 15 cos 5x. Alright, so let me write 1 by 15 plus 1 by 15 cos 5x. Sorry, 4x, right? 4x. 16 minus 1 is 15, right? Plus minus, so 2 3 4 5. 5 is odd. 25 minus 1 is 24. 1 by 24 cosine 5x plus dot dot dot. Okay, so this is our final answer for f of x. Okay, so let me check if I'm doing any mistake. Whoops, I think I'm doing a little bit of mistake. I mean, fatal mistake over here. So it is supposed to be plus. Okay, so I have checked my, actually I've done it previously, but still I'm doing the similar mistake. Yeah, so I think I need to be careful over here because this will be a fatal mistake if I'm doing this in my exam. So it's 1 by 2 pi, so minus x, which is minus pi cosine of pi, minus, so I'm doing step by step to avoid mistake. So in substituting minus pi into x there, so we have pi cosine pi. Okay, so it's not minus like I'm doing just now, right? So it's 1 by 2 pi is just minus pi minus 2 pi, because minus 2 pi over 2 pi cosine of pi. Okay, sorry, cosine of pi, right, which is 1. Cosine of pi is minus 1, right? So minus 1 times minus 1 is just 1. So it's very fatal. It will affect my mark, of course. So wait, so it's supposed to be here. Oops, a naught so it's a naught is 1 plus that sorry, f of x, sorry, it's f of x, a naught plus these chunks, right? So this is my final answer, minus that. Okay, yeah, so all good. And then the next topic is all about Fourier transform. Okay, Fourier transform. FT. Okay, so it's basically when we have a domain function in term of, for example, in term of t, f of t, usually we use f of t, and we want to change the domain into another variable or another function of the variable. For example, f of x. So how we are going to do this? So the step or the process on which to achieve this is called Fourier transform. So at first we have function f of t, which is, for example, f of t equals to t squared plus 1 blah blah blah, or sometimes you have e to the minus t plus 1, like that, and you want to change this to be something like f of x equals to, well, x plus 1 or something something something. So in terms of x, simply like that. So the process namely called Fourier transform. How we are going to do that? So it's very simple. So Fourier transform is like this with the fancy f. Okay, or fancy f of t equals to the integral, we have the normalization constant 1 over square root of 2 pi. So some books use, for example, 2 pi, sometimes use pi, sometimes use 1 over 2 pi, sometimes use 1 over square root pi, and like that. So it's just not a big deal, it's just a normalization constant. So I will stick with this kind of normalization constant. Alright, integration from minus infinity to infinity, e to the I xt dt, f of t dt. Okay, but instead, if we want to reverse this process, so we just do what calls the inverse Fourier transform. So this one we just inverse. F of t is just 1 by 2 pi integration minus infinity to infinity e to the minus I xt f of x dx. Okay, so we will get back, so this one we will get f of x as we want. So when we reverse this, so this is also equivalent to, so this is just the same thing. When we reverse this, we will get f of t back, right? Because if you see this f minus 1, which is the Fourier inverse transform, and this is Fourier transform, it will cancels out. It will give you only f of t. And also, if you do the Fourier transform of the f of s, this one, you will get nothing but f of t also. So everything is right. Okay, so one thing you need to be concentrating, or you need to be pay attention, is this here is plus sign and this here is minus sign. Okay, when you are doing Fourier transform, the thing or the function that you transforming, you will be integrating it like that. Okay, same goes with the inverse Fourier transform. Okay, because we want to get f of t. Okay, so the function that we are integrating is not f of t. Okay, it is f of x. Okay, because we are doing inverse transform of the f of s. Sorry, f of s. Sorry, f of x. Sorry, f of x. So this is f of x, right? F of x. So maybe I can use big f of x. Big f of x. No, not s. Okay, so that's my fault. Right, like that. Okay, so it's very simple. Okay, the next chapter that I've learned is Laplace transform. Okay, Laplace transform. So this is also the same thing, but here our domain is between s and t. So it is the same thing. For example, if we have f of t, we want to change into function of f of s. So what we are going to do, we need to apply the the Laplace transform. Laplacian transformation. Okay, so how? So the formula is first f of t, the Laplacian transformation of f of t. So which means we want to change this f of t into big F of s, like that. So what we are going to do is we integrate from 0 to infinity. Okay, not from minus infinity to infinity. So this is the difference between the Laplace transform and Fourier transform. Okay, e to the minus st. Okay, f of t dt. So we will get f of s as required. Okay, so it's still simple. But how if we want to do the reverse, which means from f of s we get back to the original f of t, like that? How? So for that, we need to apply the inverse Laplace transform. Fs to get f of t back. But how? Are we going to use this same formula? The answer is no. So it is more complicated than to find the direct transformation. So to find the inverse transformation is more complicated than to find the direct transformation. Okay, so for this we are going to ignore it first, because my course is not covering the inverse Laplacian transformation using formula, but instead we need to memorize some of the useful spatial Laplacian transformation. Okay, what I mean, because suppose so we don't have formula. I mean, for this for this kind of course, it is not offered to teach. Okay, so this course does not offer to teach to find the inverse Fourier transform back to the original f of t function, right? So that's why we are we ignore it first, right? Okay, for example, if I want to find the Laplace transform of t to the power of n, okay, is integration from 0 to infinity e to the minus s t times t to the power of n. Okay, t to the power of n dt. So this is make use of the integration by path. So I will use tabular method. So let's list a little bit of derivative with respect to t. D. Oops. It's not responding. D and integration. So d stands for derivative, I is integration. So I want to derivate t to the power of n, integrate e to the minus st with respect to t. So derivative of t to the power of n is n t to the power of n minus 1 n minus 1 t to the power of n minus 2 dot until n factorial time, right? T to the power of 0. So this sum e to the minus st divided by s e to the power of minus st divided by s square dot until e to the power of minus st over s to the power of n plus 1, right? Because we are derivating it until t to the power of 0. Okay, so this is plus minus, so just multiply the diagonal, t to the power of n minus t to the power of n e to the minus st divided by s minus n t to the power of n minus 1 e to the minus st over s square all the way until dot until we reach minus, we integrate 0 to infinity n factorial times e to the minus st over sn plus 1 so I will move this around. Okay, so I will separate this and that. So over here we need to evaluate the limit from 0 to infinity. It turns out that all of the terms over here will cancels to be 0, right? Because when we insert infinity to here until the last term, which is e to the power of minus st, we will get 0, right? And when we insert 0 instead, this t term will goes to 0 until t to the power of 1. So the only term which does not account for 0 when we subs t equals to 0 is the last term, which is t to the power of 0, because t to the power of 0 is 1. So this all cancels. Okay, so let's evaluate the integration of from 0 to infinity. Okay, which is insert the infinity, we will have 0, right? 0 minus, so this is minus, insert the 0, so e to the minus 0 is 1, so n factorial Sn plus 1, which is n factorial Sn plus 1 to the power of n plus 1. So this is actually the Laplace transform of t to the power of n. Okay. Hence, if the question asks us to find the inverse Laplace transform, for example, like this, the question asks us to find the inverse Laplace transform of n factorial Sn plus 1. We cannot use the formula integration 0 to infinity e to the power of minus st f of t dt. Why? Because we cannot, because that's not the way it is, right? So we cannot use like that. What you can do is you simply need to memorize the relationship between this and the Laplace transform and the inverse Laplace transform. So in this case is when we inverse this, we will get back t to the power of n, right? So the direct answer is t to the power of n. Actually, there is a formula, but it is more complex than this, so we don't have to consider in this course for a while. Okay. Okay. Next, I have learned what else? The beta function and also gamma function. So first one is gamma. Show gamma function. Okay. Function. Okay. Yeah, so gamma function is basically tells us that, so the definition for gamma function is okay, gamma of n is basically the integration, okay, from 0 to infinity. Okay, I forgot, x to the power of n minus 1 e to the power of x minus x, okay, like that. For example, if we want to find the gamma of 2, this is just 0 to infinity, n equals to 2, which is x to the power of 1 e to the minus x dx, so this is dx. So this is integration by path again, so plus x integration of that minus 1 minus 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 okay, from 0 to infinity, so that one is 0 minus 0 minus 1 over 1, which is 1, so this is 1. Okay, so gamma of 2 is 1. What about gamma of 3? So for your information, gamma of 1 is just 1, so I will add gamma of 1 here, it's 1, and gamma of 0 is infinity. Gamma of 3, let's find the pattern first, is the integration from 0 to infinity x squared e to the minus x dx. So this is plus x square e to minus x divided by minus 1 minus 2x e to minus x over minus 1 square, which is 1, plus 2 e to minus x minus 1, so it's minus here, so it's minus here from 0 to infinity. So inserting infinity, so we have 0 minus 0 minus 0. Inserting 0 is 0 minus 0 minus 1, sorry, 2, is it? So it's 2. So gamma of 3 is 2. It is 2. Okay. And if you do gamma of 4, you will get 6. And when you do gamma of 5, you will get 24. And when you do gamma of 6, you will have 120. Dot, 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 dot. So if you realize the pattern over here from gamma of 1, okay, so we don't have to consider this for a while. So gamma of 1 is 1, so 1 is just 0 factorial. So gamma of 2 is 1, which is 1 factorial. So gamma of 3 is 2, which is 2 factorial. Gamma of 4 is 6, which is 3 factorial. This is 4 factorial, and this is 5 factorial. So, with that being said, gamma of n, what is gamma of n in factorial form? So if you realize, this is 6, this is 5. This is 5, this is 4. So it is decreasing by 1 in the factorial form. So gamma of n is basically n minus 1 factorial, where n is positive integer. Okay, so that's all. So the formula over here tells you in the factorial form is basically n minus 1 factorial. So the way to remember this n minus 1 factorial is from here. So it is n minus 1 the same. Okay, so that's the tips. Alright. Several things that you need to know about gamma function is gamma of n plus 1 is n gamma n. Okay, so you can prove this using the definition of the gamma function. So it's very simple. Okay, you can prove it. And also you need to know that the gamma of half is square root of pi. And then the gamma of n plus a half is basically 1 times 3 times 5 times 7 dot 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 times 2n minus 1 over 2n square root of pi. Okay. So the way to use this formula is, so this is until n equals to 0, this is until n equals to 1, okay, and this is until n equals to, so this is n equals to 2. For example, if I want to find gamma n equals to 2. So 2 plus a half is basically 2.5, or 5 over 2, right? So gamma 5 over 2 is basically 1 times 3 times 5 until 5 only, divided by 2 to the power of n equals to 2, right? So n equals to 2 to the power of 2 square root of pi. So this is 15 over 4 square root of pi, like that. Or there's another method. Since you know that the half of gamma of half is just square root pi, so we know that the gamma of 3 over 2 is the former value, which is 1/2. So former value is over there, times the gamma of the former value of n, which is 1/2. So this is half square root pi, and then next is 5 over 2. So this is the half integer only, so it is not working for the integer. So this formula is not working for the gamma of, for example, 4 divided by 2, which is gamma of 2, gamma of 6, gamma of 3, and so on. So it is just based on the half integer, like 1 over 2, 3 over 2, 5 over 2, 7 over 2, and so on. So gamma 5 over 2 is just the former value is 3 over 2, gamma 3 over 2. Okay, I think I'm doing mistake over there. So gamma 3 over 2 is 3 over 2 times half of gamma, pi, which is 3 over 4 square root of pi. So it is not consistent with our result. Okay, so I need to adjust this. So this is okay, so we don't have we cannot subs n equals to 0 over here, so we need to start from n equals to 1, n equals to 2. So forgot about that. So n equals to 2, n equals to 3. Okay, so n equals to 2, which is 5 over 2, because 2 plus half is 5 over 2. So we just until 1 times 3. 1 times 3 is 3, 2 square is 4, so 3 over 4 square root of pi. 3 over 4 square root of pi, same. Okay, like that. And what else we have learned? Gamma function, beta function. So beta function, we have two possible formula. So for example, beta of mn is always similar as beta of, later I will talk about that, is by definition is integration. Is an integration from 0 to 1 x to m minus 1 times 1 minus x to the power of n minus 1 dx. Or the second formula is integration 0 to pi over 2 cosine 2m minus 1 theta 1 sine multiply with the sine 2n minus 1 theta d theta, and beta mn is equals to beta nm. So you can prove it using the first formula. This is the first formula. Okay, like that. Okay, And also the relationship between the beta function and also gamma function you need to know is, for example, I have beta pq is gamma of p times the gamma of q, q over the gamma of p plus q. Okay, so this is the relationship. So it doesn't matter what parameter you use, either p, q, either m, n, or anything, as long as it is constant or parameter, then it's all good. Okay. Okay, what else? We have learned about arrow function, right? Arrow function. Okay, so next is arrow function. So it's arrow function. Okay. So arrow function is defined as ERF of x is square root of 2 over pi. So this is the normalization constant. So from 0 to x, e to the minus t square dt. So if you consider this, e to the minus t square is basically the Gaussian curve. Okay, this is 0, so this is x. So usually you realize that the integration from minus infinity to infinity of the Gaussian curve dt is what? Is the square root of pi. So when you have, for example, k over here minus k, so you have, more interestingly, is square root of pi over k. Okay, so that's all about the Gaussian curve. But this is not the Gaussian curve. It is, sorry, for arrow function it is Gaussian curve, but we integrating from 0 to x, not from minus infinity to infinity. So that's the only difference. Okay. And the thing that you need to realize is the integration from x to infinity is basically the complementary arrow function, which is, oops, the arrow function complementary, or complementary arrow function, is basically integration from x to infinity, e to the minus t square dt, which is just square root of 2 over pi. Okay. Sorry. Square root of 2 over pi. Okay. Okay, a little bit of correction. So the normalization for the arrow function is not square root of 2 over pi, right? So it is 2 over square root pi. So same goes like this. So I'm doing mistake. 2 over square root pi. So how we can find the relationship between this and that is simply considering the Gaussian curve integration. So integration from 0 to infinity of the Gaussian integration e to the minus x square dx is just square root of pi over 2. Okay, and so we can break this down. Integration 0 to infinity is basically the same as integration from 0 to x e to the minus x square dx plus integration from x to infinity 3 minus x square dx. So this one we know it is 2 over square root pi sorry it is error function, but it has no the normalization constant, so it is same as error function of x. It is kind of similar, but how we need to manipulate the variable the equation. Square root pi over 2, right? Square root pi over 2 plus this one we don't know yet, infinity e to the minus x square dx. Okay, so we move things around. Square root pi over 2 1 minus arf x is this. Pi over 2, right? So yeah, it's x into infinity e to the minus x square dx. Okay, multiply both sides by 2 over pi, so this will 1 minus arf x 2 over square root pi integration x infinity e to the minus x square dx. So this thing we call it complementary of the error function, or ERFC x. Hence we can see that one is actually ERF x plus ERF CX. CX. Okay. So there is ERF CX. Error function complementary or complementary error function, right? So the graph for error function is very simple. So it's like this. So the asymptote, the x asymptote is at x equals to 1 as n minus 1 minus 1. Okay, so this is x, this is f of x, so the y asymptote. Okay, so at ERF of infinity it is equivalent to 1. Okay, so you need to know about that. Last is the elliptical function that we have learned. So this is the last chapter on the special function, elliptical. So this is very easy. So if the first kind is e k phi, this is the integration from 0 to phi one minus k square sine square theta d theta, where k is just the parameter. So this is the parameter and this is the angle. And then the second kind is, you need to know, is f k phi integration from 0 to phi the reciprocal of the function, which is 1 minus k square sine square theta. So it's just the reciprocal of the first kind, I mean the function inside the integration. So it is not the direct reciprocal, so it is not equivalent to E k phi is not just simply the reciprocal of f k phi. So this is wrong, huh? Absolutely wrong. So what I mean reciprocal is just the inner function inside the integration. Okay, and the range of phi is between 0 to pi over 2. So basically this elliptical function is basically derived from the ellipse. So so this is an ellipse. So ellipse with the perimeter or the diameter, so it has the general function of, for example, ax square plus by square equals to r. Okay, so this is circle equation. So it's a little bit differ from the ellipse equation. So a and b is the constant that differs between it is a circle or it is a ellipse. Okay, so the use of it is we can find what is the diameter or basically the perimeter of this ellipse. So first we can integrate from 0 to pi over 2. Okay, for example, the equation given is 4x square plus 9y square equals to 36 or 6 square. So we can use this, we can transform it into polar form, and then we can integrate using this first kind. I think first kind is also already enough. Okay, this is the first kind. Okay, so this first kind, you can use that, integrating from 0 to pi over 2, because the limit is from 0 to pi over 2, and then it cannot be more than pi over 2. It can be less, for example 0 to pi over 4 or 0 to pi over 3, but it cannot be from 0 to pi because that's out of the range of the limit. So from 0 to pi over 2 we have the half perimeter. Then later on we get that integration 0 to pi over 2 something dx, then we times with 2 because we want to get the entire perimeter. Okay, I think that's all for this night because I'm already sleepy. So maybe later on or tomorrow I am going to work this out clearly on how to use this elliptical function to find the perimeter of the ellipse. Okay, so that's all, and until next time, thank you.